All right, now we're going to talk about a short circuit. Most of you have heard that term, right? Short circuit. So now we want to see what it actually is. Okay, so finally, we're going to talk about a real battery. So here's a real battery. And you notice it has a little bit of resistance. You know, usually like an ohm or so. It's just really small, but I mean, that's a real battery. Sometimes when we talk about an ideal battery, we ignore this internal resistance. When we want a real battery, we include it. Okay? So this is what's called a normal circuit with a real battery. What's normal about it? Well, you know, we have our battery, we have our resistor, you know, to limit the current. All right, so everything's wonderful, you know. Okay, so delta V equals IR. Good old Ohm's law. So therefore, I equals delta V over R. Okay, so what's the voltage? 9 volts. What's the resistance? Well, here you have a 1 ohm and the same current as the 17K, so it's series, right? So I have 17K ohms plus 1 ohm. Well, is that going to be big or small? It's going to be small, right? All right, small. Okay, because this is 17,000, right? So this is 17,000 plus 1, basically 17,000, right? So 9 divided by 17,000 is small. So this is very wonderful. Nobody's going to get hurt. You're not going to melt your wires, you know. You're not going to cause any trouble. Great. Okay, now, let's say that somehow this is removed. Okay, that's called a short circuit, right? If you remove that load, this is called a load resistor. If you remove that load resistor, that's called a short circuit. And now, look, we don't have this 17K anymore, right? All we have is the resistance of the battery, which is 1. So now we have a 9 amp current. I mean, we like to have milliamps for a household, I mean, you know, for normal experiments and stuff like that. Now we have a 9 amp current. That's really, really large. We don't like it, all right? So that's what's called a short circuit, where there's no load resistor to limit the current. So if you want to play around with this, I don't suggest it, but I know there's always a few people that like doing it. You take a 9-volt battery, and I'm just explaining this, right? Here's your 9-volt battery. And so here's your plus terminal. Here's your minus terminal. If you just connect a small piece of wire here, right, there's no load resistor. So that's a short circuit. So what's going to happen? You're going to get a really, really large current, and this wire is going to become very, very hot. And so I used to do that in class, and then I decided I don't want to do it anymore because it kind of burns your finger just a little bit. All right? So that's called a short circuit with a real battery. You don't have your load resistor to limit the current anymore. Now, let's do it. Let's talk about a real example. Okay, so let's say that you're working on your car, and you have your hood open, and you have your battery there, and let's say it's a really old car. You know, nowadays the batteries have plastic caps over the terminals. Well, let's just say it's really, really old, and somehow the plastic caps of the battery terminals have worn off or broken off. And let's say you have this big wrench and you're working with a wrench. So what don't you want to do with the wrench? So again, here's the car battery. So here's a terminal and here's a terminal. So what don't you want to do with the wrench? You don't want to do this. Okay, that's the wrench, right? Because that's the same thing as this, right? That's a short circuit. And you're going to get a really, really large current, which is not a good thing. So I have a kind of a long description about this. Let's do it. A short-circuited car battery. What is the short circuit current of a 12-volt car battery with an internal resistance of 0.02 ohms? What happens to the power supplied by the battery? Well, you know, you use Ohm's law. current equals voltage divided by resistance. So 12 divided by 0.02 is 600 amps. Whoa, 600 amps. Okay, power is generated by chemical reactions in the battery and dissipated by the load resistance. But with a short-circuited battery, the load resistance is inside the battery, right? There's no other, there's no other resistor, right? Because it's a short circuit. So the only resistance is inside the battery. The shorted battery has to dissipate power, I squared R, which is 7,200 watts internally. This value is realistic. Car batteries are designed to drive the starter motor, which has a very small resistance and can draw a current of a few hundred amps. That's why the battery cables are so thick. A shorted car battery can produce an enormous amount of current. The normal response of a shorted car battery is to explode. It simply cannot dissipate this much power. Shorting a flashlight battery can make it hot, but your life is not in danger. Although the voltage of a car battery is small, 12 volts, a car battery can be dangerous and should be treated with great respect. All right, so there you go. So be careful when you work on your car. Make sure you have those plastic caps over the car battery terminal so you don't have a short circuit. Okay, now let's talk about something called grounding. Grounding. So every house has or should have a wire from the main electrical box to a grounding wire. So this goes to the main electrical panel. We have all your, anyway, it goes to the main electrical panel, then it's connected to so there's a wire, and this is a rod, and it goes into the ground. So this is called, you're grounding your circuits, okay? So that's, every house should have that. Okay, if you were here, I don't know, 5 or 6 years ago, this is the McKay, right? And so this thing was a generator. And look, it was grounded, right? So this rod went into the ground, and here's a grounding cable, right? So this was grounded, okay? Now, why do we want to do that? Why do we want to ground our circuits? So this is the circuit diagram. This is the symbol for the so this is the ground wire, right? All right, so, all right. Now notice, this is the complete circuit, right? And so there's no current going into this ground wire, right? Well, that's not exactly true. So typically, under normal everyday circumstances, there will never be a current going through the ground wire because it just goes around the complete circuit. If things go wrong, which I'll explain, then you might have some current going through the ground wire, okay? So here's the example. Okay, so let's say you live in this old crummy house and they only have these two, just pretend this is you only have a two-prong plug, all right? So old house, old equipment, old everything, all right? So here's a dryer, and this is metal, right? Metal dryer, clothes dryer. You have a two-prong plug, okay? And so, the electricity comes in, goes through something that heats up the air, and then goes out, right? A complete circuit, Great. Okay, so that's just great. Now, let's say something goes wrong. Let's say that, for whatever reason, this wire becomes disconnected to the heating element or the wire breaks or something, all right? So let's say that something goes wrong and the wire breaks and it touches the metal dryer casing. Well, that's not it. And then let's say you touch the metal casing. Well, metal is a conductor, right? So here's the electricity. Through you! And then, right? Through you, and then you're ground, on the ground. So, what happens when the electricity goes through you? You have a shocking experience. Is that a good feeling? Not at all. So, so this is a short circuit, right? This is a short circuit. And the current goes through you, so you get electrocuted, you get a shock, which is not fun at all. All right? So that's not a good thing. So what people have figured out is, hey, let's add a grounding wire. So instead of having a 2-prong plug, we have a 3-prong plug, okay? And so in other words, instead of having just 2 wires, we have 3 wires, where the third wire is just the grounding wire. So now what happens, if this breaks, the current has a choice. It can go through you, and you have a kind of a lot of resistance, or it can go through the grounding wire, which has like almost no resistance. So what's it going to do? It's going to go through the grounding wire, right? So you can see that. So it doesn't go through you. It goes through the grounding wire, which is connected to the ground, right? Okay. So it's just a safety thing, It's just an alternate path for the electricity to go through instead of you in the case of a short circuit, okay? So that's really all there is to it. Okay, great. So yeah, so you don't want to do this, okay? Let's say you have a 3-prong plug and you only have a 2-prong outlet. You don't want to take a hacksaw and chop off the grounding prong because it's just not safe, It's just not safe. So don't do that, all right? Don't do that. Another reason for grounding, like let's say your house gets hit by lightning or something like that, or there's like power surges or whatnot. The grounding wire provides an alternate path for that high surge of electricity to go through so it doesn't wreck all your equipment. All right, so grounding is just a safety thing. When we bought our house here in La Ie, we were shocked to notice that our house was not grounded. We did not have a grounding wire and a grounding rod. Couldn't believe it. So we had to get all that fixed. But it's just really, really important. Okay. Oh boy. Now we're going to do capacitors. Okay, we talked about capacitors before, how they store charge and all that. So same thing, They don't make capacitors with every single value imaginable. They only make capacitors of certain values. And sometimes you need something, let's say you needed a 10, and let's say they only make a 9 and a 1 or whatnot, So you have to learn how to add capacitors. So we're going to add them in series and parallel. So this is going to be familiar, okay? Well, we're going to do parallel first because it's the easiest, okay? All right, so here's your battery. Now, obviously, you have no idea. I mean, the current here's the current out of the battery, right? And some goes here, some goes there, some goes there, some goes there, right? So we don't know. You can't say that these have the same current. You have no idea. So they do not have the same current, all right? So what do they have? What's the same? So let me just redraw this. So here's the battery. Okay. Here's capacitor 1. All right. I'm going to draw it a little bit differently. Okay. See what I did? I just want them to be connected all the same place. All right? So if this is like a 9-volt battery, so here's 9 volts. What's the voltage here? 9 volts. What's the voltage here? 9 volts. What's the voltage there? 9 volts. Okay? So when you connect capacitors in parallel, they have the same voltage. Where have you heard that before? That's what we learned with resistors, right? So it's just true. It's just generally true. Whenever you connect anything in parallel, there's always the same voltage. All right. Same voltage. Okay, let's do it. So this is going to be a couple of chapters ago. So Q equals C delta V. That was like the F equals MA for capacitors. All right. So here we have 3 capacitors. All right, so we have Q1 equals C1 delta V, and we have Q2 equals C2 delta V, and Q3 equals C3 delta V. Again, I don't have to put subscripts on the V's because they're the same, right? They're the same. All right, so let's just figure out the total charge. So the total charge, Q total, is Q1 plus Q2 plus Q3, right? Well, let's put it in. So that's C1 delta V plus C2 delta V plus C3 delta V. So what can I pull out? I can pull out the delta V's, right? So that's going to be delta V times C1 plus C2 plus C3. And again, that's Q, right? Q total. All right, remember, Q equals delta V times C. So what's the equivalent capacitance? Just the sum, right? Just the sum. So that means I could replace these three capacitors with just one, as long as the capacitance of this one was equal to C1 plus C2 plus C3. All right? Okay, so what do you notice? So capacitors in parallel, you just add them. What was the rule for resistors? Resistors in series, you add them. Okay? So don't get confused, you know? Don't get confused. I mean, that's the part that drives people crazy. It's the same law, but it's used in a different circumstance. Okay, so that's the rule for capacitors in parallel. Let's do capacitors in series. Now, you can just guess. What do you think the rule is going to be? It's going to be the one over rule, right? But let's actually see why, because we'll learn something. All right, we'll learn something. Okay, so here we have three capacitors in series, correct? So we have the same current going through all three, and there's more to that statement than we're going to talk more about that statement later on. All right. So I'm not giving you the whole truth. Okay. So I'm just saying that the same current going through all three, and I'm going to leave it at that. But I promise you we'll revisit it. Okay, so we've got to figure out how to add these silly things. So let's look at just this thing here. Okay? So this is a wire, right? This is a piece of C1. And this is a piece of C2, correct? Okay, now notice there's no battery, right? No battery, so there's no current, so, so nothing's going on, all right? So therefore, what has to be the net charge of this thing? I mean, these are uncharged. What has to be the net charge? 0, right? I mean, there's no current. There's nothing going on. So the net charge of this thing, remember, this is a plate, a metal plate, metal wire, metal plate, right? This is just a big conductor. So it's uncharged, right? A charge of 0, okay? Okay, now what we want to do is, bang, connect a battery. So now there's going to be a current, right? And now we're going to charge the capacitors, we're going to charge the capacitors. So, so this one's going to be, plus, minus, plus, minus. No, wait a minute. The current is not going to be able to go from here to here, right? This is isolated, right? This plate is isolated from this plate. This plate is isolated from this plate. So this thing here used to have a net charge of 0. Well, since it's isolated, it still has to have a net charge of 0, right? But come on, this is a capacitor. So if this has charge plus, this has to be charged minus. Well, if this is charged minus and it's neutral, this has to be charged plus. This is a capacitor. If that's plus, this has to be minus. Right? I hope that makes some sense. Okay? So this still has to maintain the net charge of 0. It has to. Okay. So in other words, this charge has to be the same as that charge, because this has to be neutral, right? Has to be neutral. Well, if this is equal to that, okay, but wait a second, what's true about that and that? They're equal, right? That has to be equal to that because it's a capacitor. That's equal to that. I'm just talking about magnitude, by the way. So that's equal to that. That's equal to that. What has to be true about that and that? Same charge, right? Same charge. So what am I really trying to say? I'm really trying to say that this charge here for C1 has to be the same charge as C2, okay? So the thing that you want to remember is capacitors in series have the same charge, okay? Capacitors in series have the same charge. That's the big deal. So let's do it. So Q equals C delta V, right? Capacitors in series have the same charge. Okay? That's just great. All right, so let's solve for delta V. So delta V is Q over C. So let's figure out the total voltage drop from here to here. Okay? So delta V total is delta V1 plus delta V2. Let's plug in this. So you have Q over C1 plus Q over C2. I didn't have to put subscripts on the Q's because they're the same. I can pull out the Q. I have 1 over C1 plus 1 over C2. Okay, now look. Delta V equals Q divided by C, So what does this have to be? It has to be 1 over C. So 1 over C equivalent, or whatever you want to call it, is equal to 1 over C1 plus 1 over C2. So there's that 1 over rule again that we saw with the resistors, you know. All right, so what am I saying? I could replace these, I guess here I have 3, right? I could replace these 3 capacitors with 1 capacitor as long as it had this value. Okay? All right, so you got it? So capacitors in parallel, you just add. Capacitors in series, it's the 1 over rule. Resistors in series, you add. Resistors in parallel, it's the 1 over rule. So it's completely opposite. Well, that's how it is, okay? All right. So please figure this out. So here, what are these? These are obviously parallel, right? Because they don't have the same current. So these two are parallel, and then this can be replaced by 1, and then that's going to be in series with this guy. All right, so figure that out, please. So pause your video and figure it out. All right, the answer is 3.43, and I'm not going to do it for you. Do it yourself, okay? Seriously. So just remember, these are in parallel, so you're going to use that. And then you're going to have this one, same current as this one, so you're going to use that. So make sure you can do it. You should have no trouble because it's the same laws that we use with the resistors. Okay, now we're going to completely shift our attention, or topic. Now we're going to talk about a circuit, and we're going to use this later. That's why we're doing it. So this is called the RC circuit. And you'll do this in lab as well. R is the resistor. C is the capacitor. Okay? So RC circuits. So we want to talk about 2 cases. We want to talk about the first case when we have a charged capacitor, open circuit, so it stays charged, right? And then we're going to close the circuit, so it's going to discharge. So that's the first case, right, when we're going to discharge the capacitor. All right, so here, let's talk about it. Okay, again, so we're starting off with a charged capacitor. Open switch. If the switch is open, is there going to be a current? No, you have to have a complete circuit for a current. So it's not going to be any kind of a current. Now, as soon as we close that switch, what's going to happen? Well, think about it. Do these positives want to be there? No. Do these negatives want to be there? No. They're crammed together. They're repelling each other, right? So as soon as you close that switch, what's going to happen? There's going to be a current. Okay? There's going to be a current. So another way to say that, the capacitor is discharging. Now, does that happen instantaneously? No, it takes a while. Okay? So what we want to talk about is the charge as a function of time on the capacitor. All right? That's what we want to talk about. How does the charge on the plates vary with time? All right? Now, think about it. At first, there's a bunch of positives there and there's a bunch of negatives there. So as soon as you close that switch, there's going to be a huge current, right? Because, they're repelling each other, right? So it's going to be a really, really huge current because they want to get away from each other. But after a while, there's not so much positive, there's not so many negatives, so the current's going to slow down, true? So in other words, what I'm saying is there's going to be a really, really big current at first, then it's going to get smaller and smaller and smaller and smaller. All right? Okay, so what do you think that's going to look like? I mean, if we were going to graph it, well, okay, so we're talking about charge, right? But current is just a flow of charge. So like I said, it's going to be a big current at first, and it's going to get smaller, 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 So how does that look? How is that going to look? So we talked about this. Now we want to talk about this. All right? The current as a function of time. Okay? It's going to start out really large and then get smaller and smaller and smaller. So I'm not going to do the math because it requires calculus. I'm just going to give you the. Oh yeah. So that's. Yeah. Okay. So this is the answer. So this is the current versus time. And this is called a decay curve. It starts out large, then it decreases quickly initially, right? And then it starts getting slower and slower and slower. Right? It doesn't decrease very quickly over here, So why do I show you this? Because we're going to see equations like this all the time. So let's do it. Okay, so let's explain this. This is the current as a function of time. So the current, how it depends on time. I0 is the initial current, right? This is time. Time equals 0. This is the initial current. As soon as you click the switch, that's the current, right? Right then and there, right after you click the switch. So I0 is the initial current. That's why the little 0 there. Okay, E, the E from math. T is the time. R is the resistance. C is the capacitance. So hopefully in math, you've studied things like this. Like y equals e to the minus x. It looks like this. All right? So it goes really quickly initially, then it just slows down. You'll see that in all sorts of science, fields of science. That's why we're talking about it. Okay. Now, let's see. Let me show you a graph that I made with Excel. So let's just put in some real numbers. Let's say that the initial current is 1 amp, and then I have different values of the RC, all right? So I have like 1, 10, 100, 1,000 seconds. So here, if this is if RC is really small, look at it decays really, really quickly, right? I mean, it goes to 0 really, really fast. If it's 10 seconds, kind of fast. 100 seconds, takes a long time to decay. 1,000 seconds takes forever. Well, Okay. So the decay curve really, really, really depends on the value of R and C. All right, now, so obviously from the curve, the RC has tells you the shape of the curve, right? Okay, now let's do some math. What are the units? Okay, what are the units of this? Well, whenever you have an e to the minus something, this can't have any units, right? You can't have an e to the minus kilogram or you can't have any units. So this thing here has to have no units. Okay. Well, what are the units of t? What are the units of t? Well, seconds, right? So the units of t are seconds. So it has to be the units of RC, seconds, right? So honestly, that's really true. You know, if you take the ohm times a farad, you get a second. But you don't have to do it the hard way. You can just say, if that's a second, this has to be second. That's why I put these in seconds. So the unit for RC is in seconds. Okay, now, so RC has to be a time. So we're going to make the math easy. You might not think so right away, but just keep the faith. What we're going to say tau, which is like Greek, you know. Greek tau is called a time constant. That equals RC. So now the equation is this. The current as a function of time equals initial current times e to the minus t over tau. Now, why in the world would we want why would we want to do that? You'll see, right? You'll see. Okay, so here's why you do it. Because instead of having the time axis like, 1 second or 2 seconds or 3 seconds, you just put it in terms of tau. You know what the resistance is, you know what the capacitance is, so you just say like 1 tau, 2 tau, 3 tau. Why would you want to do that? Watch. So let's say that the time is 1 tau. So then you have I equals I0, E, that's equal to that to the minus 1. Well, people that do math a lot know that e to the minus 1 is 0.13. All right? So this is 0.13 I0. So it's easy. I mean 0.37, sorry. 0.37. All right? So at 1 tau, it's just 0.37. At 2 tau, we get I equals I0 times e to the minus, what? 2. And that's the 0.13. Okay? And so forth. So it just makes it easy, and you can do it with your calculator, right? You can just say e to the minus 1, e to the minus 2, e to the minus 3. It's just easier than having like e to the minus 2.457 or something like that. So that's why this is really the coolest way to write it. And you just have the axis in terms of the tau. And you're going to see this again and again, all right? So, that's how it is. All right? Okay, let's quit.